So anyways, with our next example, we're going to prove that log base 2 of 2n is big O of log base 2 of n. So just as a reminder, this is the second condition of proving smoothness. So this would be for proving that a logarithmic function that looks like this is in fact smooth. So I'm going to obviously make the presumption that logarithmic functions are asymptotically non-decreasing. So if you make that assumption, then if I prove this statement, which this is the second condition of that definition, then log base 2 of n must be smooth. Okay, so let's prove the following claim. So remember, we say what we're going to do. So let us find constants. C, which is a positive real number, right? C and n0, which is a positive integer. So remember, it's a positive integer, such that for all n greater or equal to n0, f of 2n is less than or equal to what? C times f of n. But what is this? Now, normally when you're doing these exercises yourself, you wouldn't normally write this down. You would literally write down what the function is in terms of 2n and n, respectively. But just because this is the first time I'm properly doing this with you, beyond just a constant function, I want to write it down so you have an idea what the strategy is. So this is, if I just replace that, then I'm just really saying log base 2 of 2n is less than or equal to c times log base 2 of n. So I'm going to pick c and I got to pick n0. So what are we going to pick here? So let's think about it. So what I'm going to do is I'm going to pick c is equal to 2. Why? Because I might see if I can make something out of these terms, because I know a nice property of logarithms is so-called the product rule, or if I multiply, if I have a product inside of a logarithmic term like this, so if I have something inside my logarithm, I can split on products into sums. So that's the main strategy I'm going to use here. So I'm going to try to make something that looks like that on this side. So on this side of the inequality. So I'm going to pick c is equal to 2. Then we need to find n0 such that log base 2 of 2n is less than or equal to c times, 2 times, because remember now I have picked c, 2 times log base 2 of n for all n greater or equal to n0, right? So now here's where I'm going to make my big observation. Notice that by the product rule of logarithms, now I can rewrite a product inside of a logarithm like this as the sum of 2 logarithmic terms. You'll see what I mean in a moment here. That log base 2 of 2n is going to be equal to log base 2 of 2 plus log base 2 of n. So I've split the product. So remember, this is a product in here, 2 times n. So you can split across the product here into 2 sums like this. That's the often called the product rule of logarithms. So this is the left-hand side of the inequality. And I'm going to use the product rule. So this is the product rule of logs. So it's usually a good idea when you're going to write out a chain of inequalities like I'm going to, write out your reasoning on the right-hand side, or at least across the equals or the inequality signs. Makes it easier to understand what you're trying to say. So what's log base 2 of 2? What's 1? Why? Because log base 2 of 2 is equal to 1. So what do you think I'm going to do? Well, I'm going to try to make this 1 into something that looks like a logarithmic term. So this is less than or equal to log base 2 of n plus log base 2 of n. And this is true as log base 2 of n is greater or equal to 1 for all n greater or equal to 2. So if I put in 2 into this, log base 2 of 2 is 1. And it's worth noting, like I said, that logarithmic functions are so-called asymptotically non-decreasing, but they're also technically non-decreasing, which means that either they're going to be equal or they're going to be larger. In fact, they're technically increasing, meaning that the function's value always will go up as I increase the input. This should be very intuitive. That's why I'm not writing this down, at least in our sense. I'm just taking it as a well-stated fact. Why? Because think about it in terms of the definition of what a logarithm is. Well, if I raise a base of an exponent to a larger exponent, the value of that result should go up, right? It doesn't stay the same. It always goes up. So that should hopefully be an easy enough justification, at least for the purposes of this discussion, of why this inequality will work. So I'm just appealing to the increasing nature of a logarithm. But what's this? This is 2 times log base 2 of n. And this is, of course, true for all. I'm running out of space down here, but I'm just going to finish up the sentence here. So for all n greater or equal to n, greater or equal to 2. So I would normally write that down there so it's not a part of the nice, pretty inequalities here. So what I'm going to pick for n0? I'm going to select n0 is equal to 2. So select n0 is equal to 2. Therefore, by the definition of big O, log base 2 of 2n is big O of log base 2 of n. And if you know that that the logarithmic functions like these ones, like this specific one, if you know that is in fact asymptotically non-decreasing, you can say then, as a result of this proof, that logarithmic functions such as this one are smooth. So that's the end of that proof. That box sort of melted in the microwave. Let me fix that. There we go.